multiplied by product of UV equals C, U, and V. And because of that, you can, because of the commutativity here, you can put C to that place. And also the last property saying that the product of V and V itself is non-negative. It equals 0 if and only if V is 0 vector. So that is a property, that is a definition of an inner product. Now we can see in n space we have the notion of dot product. We call it the Euclidean inner product for n space. But however, the official name for that is a dot product. And also for any vector space, the general name, general inner product will be denoted by UV between a sharp bracket like that. That is something about the notation. Now, a vector space V together with an inner product will be called an inner product space. That is, a vector space will have V plus and dot, fat dot like that. Then inner product space will be V and plus and fat dot and the inner product. So we have more thing in the definition of inner product space. Okay. Now we go to the first examples. First, the example now say require you to verify that the dot product we consider in the previous slide, in the previous series slide, that is the dot product in n space satisfy all 4 axioms of inner product. We can verify it here. Given U and V is a coordinate like that, and we define the inner product of that is dot product. Now we need to verify if that one satisfy all 4 property. The first one, in the previous slide, I show you that is some property of the dot product, and those property of the dot product is exactly the 4 property we use in definition of inner product. So you can read it by yourself at home, and then you will see it satisfy all 4 axioms for the inner product. So that is dot product in Rn is an inner product in n space. The next one, I will see the following things. Now we consider the coordinate plane R2. Now we try to define a new one, a new function. I define for, suppose that we are given U and V with the coordinate U1, U2, and V1, V2. Then we define UV between the sharp bracket to be U1, V1 plus 2 times U2, V2. You should note that that one is not the dot product, because dot product, if dot product, it must be U1, V1 plus U2, V2. But here we plus 2 times of U2, V2. But however, we claim that those function is still an inner product on R2. So you can see, I remark that it is not the usual dot product in R2, but it's still an inner product. Now we see UV to be that, and you can commute the factor V go to the before U1, V2 go to before the U2, and you get that one. And that one is V U. So the first property or the first axiom is satisfied. The second one is here. Suppose that we consider W, that is the search vector with the coordinate W1, W2. Then U multiplied by V plus W to be that. And those calculations will show you that equals UV plus UW. It means that we have the property of distributivity. Now property number C. If you take the number C multiplied by UV, you get that. So it is again CU of V. So property number C, the search property, search axiom is satisfied. And the last one, if we multiply them together, V by V, you get that one. That is obviously is non-negative. It equals 0 if and only if V1 equals V2 equals 0. So on four property of an inner product satisfied means that the special function we have just defined is already an inner product, even though it is not the usual dot product in two space. Let me explain you again. Ví dụ này chỉ cho các bạn thấy rằng nếu tôi định nghĩa một cái hàm mới cho hai vector UV với tọa độ như thế này mà tôi đặt cái UV trong ngoặc nhọn là bằng cái số này, thì cái này tuy nó không phải là cái dot product thông thường nhưng nó vẫn là một cái tích trong, bởi vì cả cái đoạn ở dưới này người ta kiểm tra cả bốn cái tiên đề, cả bốn cái tiên đề trong định nghĩa của một tích trong thì nó luôn luôn thỏa mãn. Vì thế chúng ta có được cái này là một cái tích trong. And the next one will be a general claim. Điều sau đây là một cái khẳng định nói chung, một cái khẳng định tổng quát nhất. Any inner product in n space must be of the form like that. C1 U1 V1 plus C2 U2 V2 plus Cn UN Vn with all the coefficient C1 C2 Cn must be positive. Mọi tích trong ở trong cái không gian n, không gian Rn luôn luôn phải có dạng này, với tất cả các hệ số C1, C2 cho đến Cn là các số dương. Thật vậy. The next one will show you we take one function. We are going to take a function like that, but one of Ci is negative, then it is no longer an inner product. Here is an example. We take UV to be U1 V1 minus 2 U2 V2 plus UC VC. So we have one coefficient is negative. Tôi thử lấy một cái hàm mà có một cái hệ số là âm. Then it is no longer an inner product. Why is that? Because if we choose V to be a vector with coordinate 1, 2, 1, and we take the inner product of V with V itself. So V multiplied by V, the inner product, will be minus 6. It is a negative number. So it is impossible because the axioms number 4 require that those numbers must be non-negative. So axioms number 4 is not satisfied, meaning that those function is not an inner product. It is not an inner product on R3. And also, now we continue to see what is the property of inner product. Here we have some property. I list it here for you. And we can define the norm or the length of U of any vector with those property. Let's see. the property you can read it by yourself. But now I want to continue to see on whenever you have an inner product, you can always define the length or the norm of any vector u. It is defined by the square root of that one. And the axioms number 4 requires that the inner product of u and u is always non-negative, so we can put it under the square root sign here. Or you can see that square of the length of u equals the inner product of u and u. And similarly to the previous, we can define the distance between u and v to be that. And also we can define the angle between two non-zero vectors u and v. Please pay attention that we always require that the angle can be defined only for two non-zero vectors. That is zeta, so that the cosine of zeta equals the inner product divided by the product of two lengths here, two norms here. And zeta must be between 0 and pi. And we can define also the notion of orthogonal. U considered to be orthogonal to V if and only if the inner product of U and V equals 0. So you see that now the angle, the length, and the orthogonal, it depends on the inner product. Two vectors may be orthogonal according to this inner product, but it is not orthogonal to another inner product. So it always depends on the inner product. Then also we have the notion of unit vector, and also in case V is not V is non-zero and V is not yet the unit vector, we can normalizing it. We can normalizing it to get a unit vector in the same direction, in the direction of the vector V. And here is some examples. So I suppose that we should stop our class today here, and next week we continue from this point. So that's it. Do you have any question, or we can stop here? Please.
I have two questions.
Yes.
So,
please.
Are there any relationship between the length and the absolute value?
You can imagine that the absolute value, that is the length in the case of one dimension. That is the case one dimension. The length will become the absolute value. Is it clear for you?
You mean that the length is the absolute value of dimensions?
I claim that in the case of one dimension, I mean in the R1, then the length of any vector is exactly the absolute value of that number. Because you have only the absolute value of a number. You don't have the notion of the absolute value of a vector. And
Okay.
the number that is a vector in case of one dimensional space. Okay?
Okay.
Any more question? Okay, if no, so I'd like to say goodbye to you and see you next week. Please read the slide I up on the Moodle before going to your tutor class. Okay, see you next week.
Bye bye, teacher.
Bye.
You, sir.
Bye, teacher.
Bye, teacher.